Okay. All right. So again, we are not officially starting class yet. I will give you a little bit of time at the beginning of class to do this. But if you want to get started, the quiz is open. It will close at midnight tonight. Same deal as last week. I'll give you around 8 minutes at the start of 7 minutes at the start of class to get your first submission in. If you guys have any questions, again, feel free to ask. Yeah. Sorry, what's that? Yeah. You still have unlimited submissions. Again, like I do hope this gets across to you guys. Like, I'm not necessarily trying to fail you or like make this class difficult. I want to give you a lot of content and I want to try to challenge everyone. But really, I think the midterm and the final are going to be where you will be on your own to try to figure things out. I think for quizzes, for homework, I want you guys to learn the material, not to like, I'd rather everybody get 100 on the homework and be like, we all learned it, as opposed to like half of you fail it and half passed. And then it's like, well, okay, well, now half of the class didn't learn the material, right? So I do encourage you guys to like work in groups, talk to each other, make sure you learn the material. And I trust you to like, do the right thing, I guess, there. Yeah. And that do the right thing is actually pretty nice. It comes from, I really like Google culture, if you guys ever end up working there, which I hope a good subset of you do. Every time we had a problem, they would say like, well, let's just do the right thing. So it's very trusting of people. All right, so class is officially started. I'm already recording on Zoom. All right, you guys have 7 minutes. Work through the quiz. If you have questions, raise your hand. I'll be walking around the classroom. We're just doing quiz 1 for last week. I feel like this is where all the smart people hang out. Is that true? Yeah. Yes. Yeah. Yeah, this quiz actually covers a little bit of that as well. Yeah. Yeah. No, that's great. So in case you guys didn't hear, there was a question on the homework. Reminder, big O is an upper bound. So, if you have something that's like, if you have an algorithm that takes n squared steps, it is big O of n squared. It is also big O of like n cubed. And it's also big O of 2 to the n, because big O is just giving you like an upper bound on the running time, right? So technically, when you say something is big O of n squared, you actually have an infinite number of big O's that would also work. So, yeah, you had a question? Oh, go to the click here, come to F5, and then click here for the quiz. Yeah, sorry about that. Yeah, the home page is like a little. Okay, yeah, no worries. Yeah, and that's great. Oh, the site was okay. Yeah. How do we get to the quiz? Okay, yeah, Trinity. So if you can, so to get to the quiz again, like open up the course website. And then there is a direct link to the quiz on the home page, or there should be. And this quiz will remain open until midnight tonight. It might be like plus or minus 30 minutes. So like, don't wait till the last minute to submit it, because it's like automatically closes. I don't close it. I'm asleep at midnight. Yeah. What's that? Oh, yes, that is the right quiz. Yeah, so correction, the quiz you're going to click into, it's going to say week 0 at the top. I forgot to update it. It should be new questions. So it's not the previous quiz, but yeah, so this is a typo. This should say week 1. Yeah. Okay, for okay, Jordan, I will send the direct link right now on the chat for anybody on Zoom. So this link will get you to the quiz. There you go. It should also be, if you're on the course website, when you click this at the top, that takes you to the home page. That's where you see the announcements. And that's where the quiz 1 link is. Yeah, so you're probably looking, so this is meant to cover essentially lecture 3 and lecture 4. So I think the big theta, there's like a big summary page, I think in lecture 3. Sorry, these are the notes. I believe. I believe maybe this is what you're looking for. Yeah. So I see quite a few submissions coming in. Again, the quiz is going to remain open until midnight tonight. Another way to think of the quizzes is it might be very fair game for similar questions to appear in midterms and finals. So that's why you really should try to, you should feel comfortable being able to answer these questions on your own. And there are a couple of tricky ones. So it's okay if you're getting a few wrong. Just make sure you understand why. Okay, so that's the first 8 minutes of class. Again, it's not due until, it won't close until midnight tonight. So again, you have time to come back, edit your responses. Do try to make sure you understand why certain questions are the way they are, or why certain answers are the way they are. Cool. Let's go ahead. Okay, all right, let's come back. Let's get started with lecture. Here we go. So again, quiz 1, due at midnight. You can find it on the course website. Another reminder, homework 1 is out. It is due tomorrow at 11:59 p.m. on Gradescope. Okay, 2 different submissions, one for your written answers, one for your code. I encourage you to try to submit early because the auto grader is there for the code part. So if you have bugs in your code, it will find them. Like, it won't tell you what the bug is, but it will tell you your code is wrong, right? So the earlier you submit, and you can submit as many times as you want for the coding part, right? I've had a few folks ask about interview resources. I am preparing something specific for the class, and we will make it part of like homework, etc., to get through it, just to get familiar with like tech. But since I haven't done that yet, there is a really great resource already available online. This is put together by other senior or just engineers. It's open source. It's on GitHub. It's called the techinterviewhandbook.org. The website looks like this. You can go to the getting started, and then it basically summarizes every single thing I could possibly tell you, because this website is being maintained by me, like adding contributions to it, and also other software engineers at Google, Facebook, Amazon, like big tech companies, startups everywhere, right? So yeah, it covers everything, resume preparation, etc. I will make it part of the homework eventually to cover some of this material, because I do want to encourage you guys to get jobs. I think something that I didn't realize as well is that there's a couple of folks that are not aware how much money you can make in tech. So again, like, I don't think you should always be motivated by money, but I do think there is like, 50K versus 55K. That's like not motivated by an extra 5,000, doesn't matter. But if you're talking about 50K versus $500,000, I mean, I think that changes my tune a lot, because I could probably buy my parents a house, multiple houses, right? So again, I don't think you should be fully motivated by money, but I will say that it is not uncommon once you get to be a senior engineer at a big tech company, which maybe takes 5 to 10 years for you to make $500,000 in compensation, okay? And even when you start out at a big tech company, not uncommon for you to make more than 100,000 just starting out, right? So, and a lot of that information is on this website as well. So I just want to remind you guys, this class is important, CS is important, and in general, there is a lot of money in tech. So, please, like, don't base your entire decision on that. But again, if you're debating between a $50,000 job or a $100,000 job versus the potential of $500,000, at least that was my thought process. Okay, so there are some resources there. I will also prepare some more. Another announcement for student hours. Today, I am slightly shifting my office hours and expanding them. So I'll have them from 2 to 4 on Zoom. The link is here. Our TA, Chi, is going to have them from 1 to 2 on Zoom as well today. Tomorrow, I am taking the day off, so I actually will be canceling my student hours. I am sorry for that, because the homework is due tomorrow as well. But I'm celebrating my anniversary with my wife, so we're taking that one day. We're going to Charlotte. Yeah, thank you. But yes, please come to student hours today. Again, I encourage you guys to help each other and to work together. Try to learn the material. The more you learn, the more likely you are to pass interviews, the more likely you are to make a lot of money, if that's what matters to you. All right, cool. All right, enough announcements. Let's get started, because we have a lot of material to cover today. By the way, yeah. So today we're actually going to be covering the Master Theorem. We're first going to start by remembering what we did last lecture and generalizing merge sort. So we're going to add a lot of variables to it. we're going to cover something called recurrence relations, which is like a pretty general way to think about recursive algorithms. And that is going to lead us to something called the Master Theorem, which is a shortcut for you to figure out what the big O running time is of a recursive algorithm. Okay. And this comes up quite a bit. So again, like revisiting merge sort. So if you guys remember, here's our pseudocode for merge sort down there in the corner. You guys actually wrote the code, so hopefully you remember some of this. You should feel comfortable being able to write merge sort. If once you practice and study, like by the end of this class, you should be able to write it, by yourself. So again, revisiting merge sort, because we're going to generalize from this. We're going to let Tn, so that's a function. We're just calling it a capital T because that's what we're using. It's just a function of n is going to be the running time. So from last lecture, we know that the running time is big O of n log n. We like drew out that tree. We summed everything up. We calculated stuff. We also know that Tn satisfies the following equation. T of n is equal to 2 times T of n divided by 2 plus O of n. So do folks see where this equation is coming from based on the pseudocode? Right. So I'm saying that if my problem, the total running time on a problem of size n, right, this is a function, is going to be equal to how much ever time it takes me to solve 2 smaller problems of size n divided by 2, right? So it's the same function. I'm going to do that twice. So that's why I have a 2 times, because I do it twice. Right, so that's left and right. And then I also take O of n time just to run the merge. If you guys remember, merging takes O of n. So this is like the mathematical way to write the running time of merge sort as a recurrence relation. So like I mentioned, running time, 2 smaller problems, and then the cost to merge. So more generally, you can imagine that the above, we call it a recurrence relation. That is what it's called in some mathematical terms. And the reason we call it that is because it gives an answer to this function. So it tells me what T of n is in terms of something that is small, like in terms of T itself. So that's why it's recurrence, because it uses itself to define, it's kind of like recursion, I guess. And then the key thing is that it's less than n. So the way it defines itself is in a smaller version of itself, right? Now, normally this expression is not very useful. So if you see this, you'll be like, well, if I ask you T of 100, you wouldn't necessarily know what the answer is, right? Normally, when you have a function, you have what is called a closed form expression. So closed form expression means that if I ask you, tell me T of 100, you have a formula where you just plug in 100 and like do the math, and then you get an answer. Here, you have a formula, but it's hard to get the answer immediately because you'll be like, well, let's say 100 here because it's big O of n. And then I have to plug in T of 50. So now, like, in order to figure out T of 100, I need to figure out T of 50. And in order to figure out T of 50, I need to figure out T of 25, right? So it kind of like expands out very much. So we know, so what we did is this is the recurrence relation for merge sorts. It's very easy to get this based on the pseudocode. And then we did all that work to figure out that this is the closed form solution. Because here, if I have 100, you can just directly plug it in and you get the answer, which is like 100 times log of 100. Okay, so that's a recurrence relation. Any questions on this? Is just definitions. Again, we're trying to generalize what we did with merge sort. So again, how did we solve it? So if you guys remember from last lecture, we solved it by having a tree. So we actually drew everything out, right? We said size of, the tree approach of last time. You draw the tree as it would look, and then you like add up all the work, right? So you're like, there's 2 of these here, so this is n. There's 4 of these here, so this is n. And then we counted how many levels there were, and it said there's log n of them. So that's one way to solve any recurrence relation. You can just draw it out. Most of them, you can like draw it out and then work through it, right? So let's actually try that with an example here to see if you guys are getting the hang of this. So this is a different algorithm. This is not merge sort. But you can see like what might this algorithm, what is this algorithm doing in pseudocode? If you guys like, just based on the recurrence relation, you can kind of maybe see something. Yeah. Yeah, so it's essentially splitting the input in half and then calling itself only on 1/2 of that input. And then it's saying after I call myself once, I have to do n work in addition to calling myself, I have to do n work. All right. And then the base case is T of 1 equals to 1. So formally, you need the base case. So if we try this, how much work at each layer? So we start with size n. There's n work in that layer. How much work at n over 2? So now that I've divided the problem in half, how much work do I do at this layer of the tree? Anyone?
N squared.
All right, I heard somebody on Zoom say n squared. I heard somebody say n divided by 2. Okay, yeah, so the answer here is n divided by 2. So I only have one problem that I'm going into, right? So before we had 2 problems, each of n divided by 2. That's why the total work was n for that layer. But now our layer is actually very small. It's only 1. So the total work is n divided by 2. What about here? Total work, n divided by 4. All right, so dot, dot, dot means like now we're going to generalize, right? So you can see that each time I'm dividing by 2. So the general term is n divided by 2 to the t. So how much work here? If I have one problem of size n divided by 2 to the t, n divided by 2 to the t, right? And then eventually you get down to a problem of size 1. How much work at that problem? 1. Yeah, or some constant amount, right? So if you work out this math, so the answer to this solution, to this recurrence relation would be to then add up all this work, okay? Because we have to do it for this. So this is a tree that's just a line. So it's very simple, but you would say, I need to add up all these numbers, right? And this is the mathematical notation for doing that. You don't necessarily need to be super familiar with this, but it's saying from I equal to 0 to log n, because this is how tall the tree is, right? We talked about if I'm dividing by 2 each time, the tree has height log n. At each level, I have n over 2 to the I. When I add this up, this is equal to 2n minus 1. So hopefully this is a refresher from your like calculus class maybe, or math class. What we care about is that this basically means that the running time of this algorithm is O of n. So this algorithm I wrote where I split the input in half, and each time I call myself, and then it takes me n work to put my answers back together. The running time is actually O of n. So the total work we do is actually 2n minus 1, which is big O of n, right? So again, you don't even know what the algorithm is, but because you know the recurrence relation, you kind of have a sense. So if you ever see an algorithm that does this, then now you know the running time. It's actually O of n, or you can work it out. So let's try another. So it's a little, we actually have seen this algorithm before. What's the difference here? Yeah, so now we're actually splitting. So we're still dividing the problem in half, but now we're doing 4 problems. So at one level, we split into 4, right? Wrong tree. Why is it doing this? There we go. Sorry about that. That was the wrong tree. This is the right tree. So again, we start with the problem of size n. How much work do? We just do n at the very beginning. Plus, we call ourselves 4 times. Each problem does n divided by 2 work. So in total, we do 2n work. You can do it again for 4. Total, you do 4n work. And you say like, okay, here's my pattern, right? At each level, I do 2 to the t, n. And at the very bottom, I do n squared. So this is actually that algorithm we covered in lecture 1, where it was like divide and conquer for multiplication without any tricks, right? Yeah, question? Yeah. T2 is just like, it's just a letter. I'm just calling this the function, but it's supposed to be the running time. And all I know about this algorithm is that I can define the running time as my running time on n is going to be, I'm going to call myself 4 times on n divided by 2. And after I call myself, it's going to take me n steps to merge my answers together, right? So again, this is like very useful for recursive algorithms because you can very easily write this formula, and then you can forget about the algorithm. Then you can just, do the tree and try to figure out like how much running time it takes. So if you do this tree, again, the math, you don't necessarily need to know all of it. In the lecture notes, I explain in more detail. If you work all this out using geometric sums, etc., it does come out to be n times 2n minus 1. Which is big O of n squared. Okay. The thing that matters here is that's big O of n squared. and for you to like get a sense of like, if I have a skinny tree, it seems that most of the work happens at the top. If I get a tree that is getting really wide, it seems that most of the work is coming from the bottom, right? Because here at the bottom, we did exactly n squared work. And it turns out our big O running time is O n squared, right? And then in the previous example, we did n work at the very top. That was where we did most of it. And it turned out the running time was big O of n. Okay, so here's actually more examples that you have seen in class. So this is the one we just did. This is the one for merge sort. And this is actually the one for caret suba. So the difference is that you have 3 subproblems. And when you work out the tree, we said it was like n to the 1.6. Okay. So we have done all of these in lecture already. Does anybody, I mean, you don't actually have to have an answer to this, but does anybody see a pattern that might come out? Yeah. Yeah. I think maybe the easiest one to see the pattern for, there is a pattern for this one, for example, because if you say like you have a 3 here and you have a 2 here, and then this is n to the log base 2 of 3. So it's like, I don't know, those numbers somehow like made it into the final running time. And then similarly here, this is n squared, but if you think about it, it could be like n to the log base 2, because I'm dividing by 2 each time, of 4. And that's actually 2. So these two are kind of like, it looks like maybe you just take these numbers and plug them in here, right? Or something. This last one's a little weird because if you do the same thing, you would get, you know, log base 2 of 2, which gives you 1. But this is like n, it's not n to the first, it's like n and then there's log n, right? So that one's a little different, right? But yeah, if you guys like this, you know, you practice it and then you sort of maybe notice patterns. There is a pattern, and I will give it to you. So again, this probably took some researcher like many years to figure out. You guys are just being taught it, so you're kind of like expected to know it. But essentially what we're gonna do is we're gonna, like we said, those numbers A, B, and then we're gonna add this number D, so the total amount of work to merge problems. And we're just gonna call them variables. So these are not, they don't depend on n, so they don't actually change with our problem size. But instead of using 3 and 2 and like 4 and 2, we're going to use letters so that we can make it more general. So what this says is, suppose you have a recurrence relation of this form, right? Then your running time, you don't have to draw the tree. Here's the shortcut. Here's the answer. Okay. So again, Master Theorem is the shortcut. So you don't have to draw the tree. You don't have to do the math. You don't have to add everything up. So you should know how to do that because sometimes this doesn't work. But a lot, 95% of the time, this is how you would figure out. You would look at your algorithm, write the recurrence relation, and then you would look at A, B, and D, and you would say, okay, if A is equal to B to the D, my running time is this, n to the D log n, okay? If A is smaller than B to the D, my running time is this, et cetera, et cetera. So we're actually gonna prove why this is true to give you better intuition. But does everybody agree this maps with like what we saw with the 3 examples we just talked about? So for example, for merge sort, well, actually, I don't know if I have slides for it, but any questions on this? So this is the main takeaway from today's lecture. This is called Master Theorem. If you have a formula like this, then the running time is big O of this. So you can immediately jump to a closed form solution for your recurrence relations, okay? I actually don't normally remember this formula. You usually look it up. So on exams and stuff, I'll probably give it to you, but you need to know how to use it. So you need to know like what the A means, what the B, what the D means, right? So yeah, those are a lot of symbols, but this is the main takeaway from today's lecture. So, you know, snapshot that or something. Again, so we walk through it. So A is how many subproblems I have. B is how much do my subproblems shrink, right? So far we've only seen B of 2, which is we always cut the problem in half. We will have, at the end of this week, we will cover an algorithm where the problems get split into like 1/3 and like 7/10 or something like that. It's called median selection if you guys want to get ahead of class. And then D is how much work, that should say work, not word, how much work we need to combine the solutions. So in all the examples we've seen, the work is linear, but this is saying like, oh, sometimes you could do like maybe n squared work to combine the solutions, or n cubed work. So as long as your algorithm can, as long as you can make it match this formula, then this gives you the answer. So again, back to our examples. So the first one that we had was needlessly recursive integer multiplication. So this is not Recursive. This is like the one we covered first. And if you look at it here, you have your A is 4, your B is 2, and your D is 1. So this is how you use Master's theorem. And this is what you might be asked to do in homework assignments, which is like, here's the recurrence relation. What is the big O running time? So the thing you do is you look up for the A, B, and D. So here you notice that A is bigger. So I copied it over here for reference. So you notice that A, which is 4, is bigger than B to the D. So B to the D is 2 to the 1. So that's 4 is bigger than 2, right? So the running time by Master's theorem, so A is bigger than D, so that's this part here, says that the running time is big O of n log base B of A. So log base 2 of 4. So that gives you n squared. So you don't even have to draw the tree, right? Now you have like a formula, I guess, to give you the answers, right? If we go to Recursive, you notice the same thing, which is A is 3, and then B to the D is 2. So 3 is bigger than 2. So it's going to use that same formula from above, where we take n to the log base 2 of 3, right? So that's using this last case for those two. All right. Again, if we keep going with this, so for merge sort, we have A equals 2, B equals 2, D equals 1. Right. So if you plug it into the formula, what do you get? Which case am I in? First, yeah, you're in the first case. You get A equals B to the D. So you get 2 equals 2, which tells you that the running time is n to the D, which in this case is 1, log n. So the running time is n log n, right? And we already knew this, but I'm showing you like this is how you would do it. What about this one? So we haven't, this is the one we did for practice just now. We have, which case are we in this case? You're in the second case. So what's the running time? Well, I guess I gave it to you, but it's big O of n, n to the D, right? And D is 1. So big O of n, right? So that's Master theorem. That's the main thing you need to know. And what we're going to do in lecture today is we're basically going to prove it. We're going to show it's true. And the way you prove it is the same way that we did for merge sort. But instead of having specific numbers, we're going to use the letters A, B, and D. All right. So yeah, it's exactly the same thing. We draw out our tree. So in general, this is what the tree looks like, right? So you guys already did trees with 2, B equal to 2. So obviously I didn't draw out all of the problems. There should be like A of these problems, but like, how do you draw A? Well, I just do 3, but there should be A of them, because in general, at each factor, we have A problems, and each one gets smaller by a factor of B, right? So that's the tree. So let's see if we can walk through this. So here's the answer to the first one. I'm at level 0, my number of problems is 1, and the size of each problem is n. How much work am I doing at level 0? N. Oh, I didn't ask that. Okay. What about for level 2 or level 1? How many problems and how big is each of them? Remember, this is a general case. So even though I drew 3 of them, that's not, yeah. Yeah, so you have A problems, and each one is of size n divided by B, right? Cool. What about the next level? How many problems do I have, and how big is each problem? Yeah, so each problem is of size n divided by b squared. So that's right. And then how many total problems do I have? A times A squared. Because for each of the problem above, I get A more, right? So that's A squared n to the b. Now, dot, 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 maybe you guys can work out some more examples. But in general, at level T, how many problems do I have? A to the T and each problem is of n over b to the t. So again, we did this for merge sort, so now we're just plugging in letters. And at the very end, how many problems do I have at the very bottom? A to the log base b of n. Yeah, a to the log base b of n. Each problem is of size 1. And this is level log base b of n, right? So the last level is, so we are actually using log base b here. In general, when I say log, it's log base 2. But in this case, like it actually matters because like each time we're dividing n by b, right? So log base b of n just tells me how many times can I divide it by b before I get to 1, right? All right, so now we go back. So how much work am I doing at each level? So how much total work do I do at level 0? You do n. Oh, I guess like you guys can think about this. I'll give you guys like, I don't know, 30 seconds to think about it. Shouldn't be. Discuss with each other, maybe say hello. And let's do like all the levels. Can you guys do all the levels? Yeah. Let me check if, oh, okay. Well, let's go ahead and do it. So how much work are we doing at the first level? Yes, O of n to the d. So in this case, I'm gonna replace O of n with a c just to make it more concrete. Like c is like the constant that big O hides, right? So the amount of work is c times n to the d, right? Because again, our relation is not n, it's that we might take n to the third power to merge things or whatever, right? What about the next level? A times c times n over b to the d, right? So I have a problems. Each one takes n over b to the d power, right? Because that's coming from here. And then I have an extra c just lying around. Okay. So again, similarly for the next level, we have a squared c n over b squared to the d. So again, I'm just, you're using a lot of letters, but you guys did like already do this for merge sort. It's just now we're saying like, it's not just for merge sort. Let's do it for every single algorithm out there that follows this recursive relation, okay? The most complicated one is this one. Again, you don't necessarily need to remember all of this, but you need to understand where these numbers are coming from, right? So I'm basically number of problems multiplied times the size of the problem plugged into this formula, right? And then at the end, we're going to assume that T of 1 is 1, but you get A log B to C. All right. So now if you wanted to answer what's the total amount of work that you do, you would add up all of these like variables. So again, it's a lot of math. The total amount of work is essentially this. If you like add it up from t equal to 0 to log base b of n. Again, I'm not going to ask you to reproduce this on an exam, probably not a homework, but you can imagine if you were writing this, this is what it might look like. And we're going to use it for the rest of the lecture slides. Okay, so this is just saying each of these being added, right? Where I'm using this big sigma notation to be like, you know, t equals 0. That's the first example where I have c times n to the d, and then this becomes 1 because anything to the 0th power is 1, right? So that's the first one, plus c times n to the d, and then I take a divided by b to the d to the first. So there's a, b to the d. So I'm just simplifying all the stuff that we worked and writing it in one formula, okay? And that's the answer actually. So that's how much work it takes, and this is the formal proof of Master Theorem, right? Because you did it in the most general case with this tree, and you wrote this complicated formula for what it should add up to, okay? So now the thing that we have to do is we just want to check each of our cases, right? And this is actually where the cases come from, because we're going to see that this is why we compare A and B to the D, because it matters what's inside this parentheses as to what this sum is going to equal to. If you guys remember geometric sums from your math class, this is coming back to that, okay? So again, like what we're going to do is we're going to check each case. So we'll start with the first case we have here, which is A equal B to the D. So that means that inside this sum, this is equal to 1, right? And 1 to any power is always 1, right? So when I sum from t equals 0 to log base b of n, what does this sum become if everything inside the sum is 1? Yeah, back there. Log, yeah, what was that? Yes, this part inside becomes just 1, but I'm summing multiple ones, right? Yeah. Log base b of n, yes. You're off by 1 because we have a 0. We start at 0, but that is correct. So this is what I'm saying. This part becomes 1, and then when I sum it, I get log base b of n plus 1, right? Because this is saying 1 plus 1 plus 1 plus 1 plus 1, you know, this many times, right? See that? And the number of times is log base b of n plus 1. The plus 1 actually doesn't matter. So even though you might not be perfectly correct, it actually wouldn't matter for your final answer, because this is, again, like, I don't know if you guys remember your log formulas, but you can, if you have log base b, you can simplify it as log n over log b. Like, it's a change of base formula. I think that's what it's called. But again, the reason I'm doing that is just to show you that the base of the log in big O notation doesn't matter, because log of b, this is a constant, so it gets thrown away anyway, right? So this shows you that for the case a equal b to the d, your running time is n to the d log of n. So quick question for you guys: why am I using big theta here? What is the difference between big theta and big O? Yeah, back there. Yeah, this is both an upper and a lower bound. So in industry, you mostly use big O because people tend to just care about, like, what is the worst? You know, can you give me something that my algorithm will definitely not be slower than, right? But in this case, this is actually like, it's exactly equal to this function, right? So big theta tells you that this is a tight bound. So it is both an upper bound and a lower bound. So it's basically saying my function grows like, it is not equal to this function, but it grows essentially the same rate as n to the d log n, right? Cool. All right, next case. So a is less than b to the d. What does that mean? That means this part is what? Less than 1, right? So we're using the formula from before, but we're simplifying it. If it's less than 1, do you guys remember your geometric sums? Not too well. Don't worry. A lot of the details don't matter because we're going to use big O. So we're going to brush over a lot of details. Again, I won't necessarily ask you to reproduce this, but this is the type of stuff that, like, I have, like, I think the first team I was on, I actually had to do this for one of the new algorithms we wrote. So you don't have to do it, but there are sometimes times when this information becomes useful, right? So again, back to geometric sum. So geometric sum is just summing, some constant x to the t, where t is the index that I'm going by, right? So if x is less than 1 and greater than 0, this is what the sum ends up being, right? X to the 0, x to the 1, x squared plus dot 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 x to the n. The x to the 0th power is what dominates in this summation. Because if you have something smaller than 1, the more you raise it to a power, right, the smaller it gets. So in the big N case, this is going to be mostly the initial terms. Another way to think about this is that if you have less than 1, it sums to a constant value. So this is the case where a geometric series converges, if you guys remember that from calculus. So the running time is constant, actually, right? Now, if x is bigger than 1, so this is just the x. So x to the 0 is going to be 1 because anything to the 0 is always 1. Yeah, so this is always 1 plus stuff, right? But this is saying if the number I am raising to the power is less than 1. So this could be like a third. And this is going to come in handy because in this example, this thing, we're saying it's less than 1 because we're in the case where a is smaller than b to the d, right? So, but, hopefully you guys are seeing oh, if it's less than 1, then I don't care what it adds up to. It's basically going to add up to some constant number, right? In the big N case. If X is bigger than 1, then as you raise to a higher and higher power, X gets bigger and bigger, right? So this is like, 5 to the first is 5. 5 to the second is 25. 5 to the third, 625. 5 to the fourth is like more than that, So what this tells you is that the last term is the one that dominates, right? So this is actually theta of x to the n. It actually doesn't matter what the beginning terms are. At the end of the day, the one that's going to matter the most is going to be the last one, because that one's going to be like a trillion. And then the rest of them are going to be like a trillion plus 5 million. And you're like, it doesn't make a difference, right? Okay, so going back to our case here, if it's less than 1, what do we know? What do we know about this whole summation if this is less than 1? It's some number, right? And for big O, we actually, you can work it out. You can figure out what the number is. It's like a really complicated formula. Not that complicated, not more complicated than this. You could figure it out, but it's just some constant. It's going to be some constant. So that means that the running time is theta of n to the d, because I have some constant times some constant times n to the d, right? So that is this case where we are here, right? Does that make sense to everyone? All right, so you guys are proving the master theorem. At the end of the day, you're just going to use it probably, but this is how you would think through. And this is why, I think the prereq for this class is like some math class or something. Math does come up in computer science quite a bit. So the next case, again, is where a divided by b to the d is larger than 1. What we said last time is that the last term is the one that's going to dominate, right? So we can actually replace this with the last term in the series. So instead of taking all the sums, I'm saying all the earlier terms are not going to matter. The last one is the only one that's going to matter. So that's why I'm replacing it just with this. And that, I said we'll do it on the board. Just trust me, this simplifies down to this. It has a lot to do with exponent rules. You can come to student hours. I'll try to explain it to you if it doesn't make sense to you. But basically, you distribute this log into the fraction, and then this n to the d ends up canceling with an n to the d that pops out down here. And then you get a to the log base b of n, which is the same as n to the log base b of a. So again, if you do some exponent things, it turns out to be the same. So you don't necessarily need to know the math, but that's essentially how the third case works out. So now we have, you guys, I guess, have oh no. Wait, can folks on Zoom still hear me? Oh, they say yes. Okay, so I don't know. I got a message about it not here, but it looks like it's working. Again, this class is optimized for in-class. So as you guys can see, I talk to you more. I talk to the folks on Zoom. So anyway, you guys checked all these cases. This is the master theorem. And again, why are there 3 cases? We can walk through, I guess, now to give you a little bit of intuition. So that's a bunch of math, but now to give you a little bit of intuition as to what's going on. Again, like we said, A is the number of subproblems, B is how fast they shrink, and then D is essentially a proxy. The bigger D is, the more work it takes to put them together. The bigger B is, the faster they shrink. The bigger A is, the more problems you get, right? So there's a trade-off. That's why you have all these cases, because there's essentially a trade-off between them, okay? Essentially, this boils down to there's a struggle between, if you do a lot of branching, so if you have a lot of subproblems, so if A is very large compared to B to the D, so A is bigger than B to the D, then most of the work gets done at the bottom of the tree, okay? If the problems are small, so A is small compared to B to the D, so you have a very shallow tree, very kind of straight down, then most of the work is done at the top of the tree. And we actually saw examples of those 2 cases. So again, we did, so this is an example of a tall and skinny tree. That means A is less than B to the D. So the amount of work done is mostly at the top, right? For a recursive tree, so this is one where you have a lot of more problems than work, then most of the work gets done at the leaves. So that you get O of n squared. And then the other part is merge store. This is where the two cases are equal. So this is why you have three cases. It's kind of comparing the different types of trees, right? Where they're exactly equal, the work gets like evenly distributed throughout the tree. So you end up doing exactly the same amount of work at each level, and there's log base, log of n level, so you get O of n log n. Okay. And I think that's it for today. So so again, like the main thing you want to remember is the master theorem. So this is a technique for solving recurrences. So if you look at a recursive function, it should be easy-ish for you to write a recurrence relation for that. Because it's just like, how many times am I calling myself? And then how much work do I have to do to put them together? And then you can immediately use master theorem most of the time to get the big O running time of that algorithm. Okay. Because recursive algorithms are tricky with big O because it's not like you're just counting like the number of for loops or stuff like that, because you're calling yourself, right? So that's why they get a little tricky, and that's why you need master theorem. Next time, we're going to learn a different, more advanced method for solving these recurrence relations. And that's it. Yeah. Wow, right on time. Great. All right. I know this, so last lecture, we did a lot of coding. This lecture, it's a little bit more math heavy. Again, I have used this before, not all of it, but I have used it before. How is the pace for folks? Like for a lecture that's more heavy on the math, can you guys are you guys following along? Do you see what's going on? Kind of in the middle. How does this compare to like a coding lecture where did you guys follow along better on that? Yeah, okay. Yeah, because you can see the code, right? Yeah, so I will be doing a mix of both lectures. Again, this class, I guess one of the reasons it's considered like really hard is because there is a lot of math that gets involved for the algorithms we cover. But I will do a mix of coding and whatnot. Reminder, the quiz is due at midnight tonight. It's 12:50, so you guys, I'll stop sharing. And everyone on Zoom, thanks for coming. I'll drop from the call.